All right, guys, welcome. Thanks for coming. My name is Matt. I'm going to talk today about modernizing the data center and specifically about hyperconvergence and the network's role in that. So there's a lot of talk here at the show about hyperconvergence. I think it's really a great topic. We're at Plexxi, we're firm believers in hyperconvergence, and what we're seeing right now in the industry is a lot of customers or a lot of IT people are looking at hyperconvergence and starting out small for a specific workload that might be normally something that's harder to deploy. Maybe it's a VDI, maybe it's big data or something like that. And they quickly see the benefits of it and want to expand it to take over larger parts of their data center. And they quickly run into some networking issues with that. So that's really what I'm going to talk about today. I'll start, since we're talking about hyperconvergence, let's talk about it. I'm not going to define it in detail, but this is nicely scoured from the web. Pretty simple, right? Network, storage, and compute in a single platform, all converged. But you notice here, right? You got your storage and compute block, and this is your network, right? The Ethernet jack that comes out of it. That's it, right? That's all you need, right? No? Sounds great. So obviously storage and compute are a big part of hyperconvergence. The network part is still something that people have to deal with, right? You don't go and start to string together a bunch of Nutanix appliances by daisy chaining Ethernet cables to each other, right? I mean, that is not really workable. You actually have to build a network to connect them. So what we see is a lot of people running into this problem where as they get into that mode where they say, okay, this is really cool, let's go beyond that first workload. Let's get to multiple workloads. Let's mix some OLTP in with our VDI. Let's do some big data. Let's start to leverage this thing because we're using it and the cost savings are dramatic. Then they get into okay, now we have to build a network fabric to connect these devices together because now we're in this kind of multi-rack deployment scenario. And they look out there and say, okay, well, we got to build an MLAG fabric or a leaf and spine. And you start talking about things that really you need a networking specialist or a networking team to go and do a network to engineer for you. And you start to get into this domain of, okay, now we're just erasing all the gains we had from all this simplicity, right? Because network engineering is hard. It's a reason it's one of the last siloed domains out there, because once you start talking about protocols and how to tweak them to get your network to do what you want, you have to be dealing with people that have done this and are specialists in it. So when we talk about what the network's role in hyperconvergence is, we're really talking about three things. One is not to undo all the convergence that you just gained, right? So the fact that we've gained all this benefits from converging, the simplicity, the scale outness, all that kind of stuff, we want to be able to keep that going as we expand that deployment. We want a network that scales linearly, just like the converged blocks do. The second thing is you want to be able to create separate networks for compute and storage workloads with this notion of dynamic dials. And what I mean by that is convergence is really good from the simplicity perspective, but there's also benefits of keeping things apart, right? There's a reason why we had dedicated SANs. There's a reason why people build dedicated infrastructure if they want really deterministic performance for a certain application or certain things. The best way to do that is keep it in its own infrastructure. But again, when we're talking about convergence, we're starting to mix a lot of things together. So what we want the network to be able to do is give you the benefits of convergence, but also have the ability to partition out the things that you want separated in that converged network fabric, but give you the dials to turn up and down each one. So if I need more compute in this part of the network, or I need more storage in this part of the network, meaning from a network bandwidth perspective, I have those dials available to me. And the third piece from the network perspective is as seamless as possible integration into the management domain of the hyperconverged stack. So when we partner with folks like Nutanix or SimpliVity or the hyperconverged vendors, we do everything we can to bring our network management information into their platforms. So dashboards directly into Prism, for example, is something that we do. So as much as possible, your focus is on deploying the cluster and not on a separate siloed networking domain, right? That's really important for us. So a little bit about who Plexxi is. We build If you haven't figured it out yet, we build data center networking solutions with a specific focus on IP storage and hyperconvergence. So, and that's kind of in the spectrum of convergence. So we see people that are looking at building modern data centers they're getting rid of their SANs, so they're converging to a degree. They're moving from fiber channel SANs into IP-based SANs, and they're trying to run everything on the same Ethernet-based network, Ethernet-based IP network, all the way up to full hyperconvergence, where they're melding the compute and storage like we talked about. And what we do is we build a data center networking solution for those folks. We call them cloud builders because they're generally, their focus is less about building a specific operational domain like compute and storage and networking. Their focus is really get the infrastructure up and running so it's providing services as quickly as possible, right? So they're looking for ease of use, simplicity, things that work well together, and they don't want to spend a lot of time with storage administration, network administration, compute administration all separately. We have 3 parts of our solution that we sell. We do sell switches. These are Ethernet-based switches. We build our own. They're completely standard Ethernet based switches, so very similar to the ones that you'll see from other vendors like Juniper and Cisco and Arista. All the same protocols, all the same technologies from an interoperability are supported. We also work with what we call white box switches. So if you have, if you want to use switches that are completely off the shelf standard, our software will work with those as well. So the reason we build our own switches is because we can actually build into those switches an element of simplicity from a cabling perspective. So we can allow you to build a network very simply, rack by rack by rack, just by clicking switches together with essentially 1 or 2 cables. And it turns out that cabling complexity is one of the big problems that people have with designing networks. Not just from the perspective of there's a lot of manual labor involved, you have to go actually plug in lots and lots of uplinks to different types of switches, you have to configure protocols, you have to now manage all those protocols and all those ports. But you also introduce a lot of opportunity for error. And some of our customers say, 20 to 30% error rate just in cabling. And you can spend weeks to months going and figuring out what happened, and it was some guy plugged the wrong port into the wrong port. So our own switches have a lot of built-in cabling simplicity where you literally just daisy chain switches together to build your network. We have a piece of software that is our control plane, and that allows you as a user to go tell the network what to do in language that isn't networking speak. So you can say, I have a workload that needs a lot of bandwidth, or that's really latency sensitive, or that needs to be isolated from other workloads. You can tell it to the control plane in those words. And it will go and figure out all the things underneath that turns into in terms of networking specific or device specific information. And then we have a whole section of our solution called Plexxi Connect, which is our integration plane. This is, again, software that allows either the user to build integrations into the systems that they use, whether they're custom applications or vCenter or OpenStack, or lets us as a vendor to pre-integrate into very popular systems like, again, Nutanix Prism, VMware, vCenter, Hortonworks. We build a lot of these integrations ourselves because we can look at those applications or those orchestration systems and understand what they want from the network and how they would want to use the network and pre-build a lot of integrations for our customers. So those are the 3 aspects of our solution. I'm going to jump back to those 3 things that make the networks or define the network's role in a hyper-converged data center. So the first thing we talked about is a converged network, right? So we talked about the notion of a leaf in the spine. And if you don't know what that means, it's essentially think about a multi-tier data center network. So in every rack of compute nodes or hyper-converged nodes, I have a top-of-rack switch. Somehow those top-of-rack switches need to talk to each other. So generally what happens in most data centers is you have to build another tier of switches just so your top-of-rack switches can talk to each other. And again, that becomes where all the complexity starts to creep in. And now you're talking about going from a hyper-converged model where everything's literally scale out. You buy what you need when you need it, and you add more when you need it, to a model where you really are talking about scale up. So to build a leaf and spine, you need to think about how big is this thing going to be, and you need to buy that spine layer as big as you can possibly afford, because if you outgrow it, you need to rip it out and build another one, right? That's some of the complexity that comes in there. So we wanted to build a converged network that has really no leafs, no spines, no protocols. It's just one type of switch. It sits at the top of your rack. It connects again to other switches and other racks very simply. It grows as you grow. So you build a rack, you have 1 or 2 switches. You build your next rack, you have a couple more. You don't have to pre-build anything, and you just keep going like that. Again, this is kind of the alternate model on the left, where you see you have to build this multi-tier network, you have to cable it all, you have to understand the protocols. Now, the biggest downside is really this is a static network. It's wired in a certain way, and it's wired to basically do one thing, which is try to distribute the traffic evenly across those set of uplinks. What we think is that once you've built this flat single-tier network, it should also be really dynamic. So the amount of bandwidth that you need at any given point between any given rack in your data center should be up to software, not up to how you wired it when you started. So that's the key aspect of the way we build our network, is really this notion of dynamic wiring versus static wiring. The second aspect we talked about was it needs to give you a converged network, but still give you the benefits of isolation, because some applications just need to be isolated. Storage is a great example of that. Storage has what's called the noisy neighbor problem, right? It's all of a sudden a file system or some type of cluster or array needs to exchange traffic with the other members, and storage has a lot of traffic, right? It generates a lot of traffic. You're talking about petabytes of data that needs to be exchanged, and that creates impact on other traffic that's in the network at the same time. That's the noisy neighbor problem. So generally, that's why SANs were always their own thing, and that's why if you read the best practices of IP-based storage systems, they generally tell you build a dedicated physical network for this, because there's going to be a lot of bandwidth and you don't want it to impact everything else. So we want that benefit of isolation on that converged physical, and that's what our network does. It gives you the ability to essentially define by wires what the inter-switch bandwidth is doing at any given point in time. So for example, in a hyper-converged world, the first thing we do is understand that there are storage VMs that are going to talk to each other, because they're building a distributed file system, and they're going to be talking all the time. And every time I write a file, it's going to be written across the cluster. Every time I remove a node, it's going to rebuild the file system. All that traffic is going to go over my network. It's probably best to keep that isolated. And when we say isolated, it means give it its own set of physical wires across that network. So that's one of the first things we do. And then the other things that we want to look for are the temporary events that will create a lot of bandwidth. So again, that notion of I got to rebuild my cluster all of a sudden because I added or removed a node, that's a temporary event. I don't need to have bandwidth there all the time for that. But when I detect that's happening, I want to make sure there's enough so that it doesn't bleed over and it doesn't slow down its own performance, and it doesn't impact other traffic. So our networks, through software, by talking to the hyperconverged vendor management systems, we can understand what those things are and build the isolated network for the file system itself, and then detect these events as they're happening. So just a little background on this. We know, in general, we know the fiber channel model is slowly changing or evaporating. Not evaporating, it's declining, right? Most people are moving from these traditional dedicated storage networks into either what are called server SANs, which is really just the software equivalent of hyperconverged, or converged IP fabrics. We know this is happening, and we know there's a large trend along these lines. And what a lot of people don't realize is that, again, when we had, in these old worlds, in these storage area networks, that traffic was all hidden by the SAN, right? Again, these are storage arrays that are part of a SAN. There's a lot of stuff that's happening in these storage arrays that are hidden by the SAN directors and the things that are constructing that SAN network. So again, metadata synchronization is one big thing. Like, a lot of the traffic that is actually generated in the SAN isn't just the data that you're storing or retrieving, it's the data between the nodes that's happening. The metadata sync, replication, backup traffic, all that kind of stuff happens in the SAN. So when you take that SAN away and you start to put it on the same fabric, you start to see these problems. Again, it's not just the amount of traffic that you're storing and retrieving, it's all this other traffic that's happening when you move this traffic onto your Ethernet network. And so this problem gets worse with hyperconvergence. It gets worse from the perspective of even with an IP-based SAN, I still have the option, even though it's expensive, I have the option of creating a separate physical IP network for my storage traffic, right? I put 2 more NICs in my servers, I connect them to a separate set of switches, and all my storage traffic is always over that network. Once you're going hyperconverged, you start to mix this traffic, and it becomes harder and harder to pull it apart by physically separating your network. So this is really what we want to be able to enable in the network. And this isn't a new phenomenon. We saw this before in virtualization. When in VMware's own best practices, they tell you, hey, just to run a virtualized network, there's a lot of infrastructure traffic, right? There's vMotion traffic. There's the virtual machine traffic itself. There's management traffic. There's IP storage traffic. And there's fault tolerance traffic. All of these are, again, if you look at the best practices, isolate these all from each other. Why do they say that? Because they want predictable performance. The more you mix this stuff together, the more you get into these problems. So we see the same thing happening again with storage traffic, and it's probably a 10x problem from a network traffic perspective, because again, when you look at storage traffic, the amount of traffic that's generated just by the data that you're generating is only a small percentage of the overall traffic that's generated by that storage system because of all these other things that the storage system is doing. So again, we want to get to this notion of many networks versus one. We don't want all those things to be separate, physical, isolated networks, and we don't want them all mixed together, colliding over each other. We want the benefits of convergence, performance of isolation. That's really what we're trying to build here. The third piece, again, is this notion that we want to remove the necessity for dedicated siloed management for the network. Once you go hyperconverged, you're already kind of down the path of converging compute and storage administration. The next layer beyond that is how can you make the network operations as easy as possible? Again, when you talk about traditional networking, you're talking about very specialized skill sets. But the biggest issue with network engineering is that it's really focused on how you do things relative to a given network device. So how do I engineer a Cisco network? How do I engineer a Arista network? All these things are device-centric type of mentalities, and really somewhat an order or two removed from what the business is trying to accomplish. So if I'm trying to deploy an application, I'm thinking about things that are not related to setting a parameter of a protocol in OSPF or BGP, right? Those two things are degrees separated from each other. It's hard to correlate the two. So what we want is as much of that to be hidden because we can take care of those details through software and let the user focus on telling you what they want to accomplish, not how it's done. That, again, now makes the user a lot less reliant on specific vendor implementations and more focused on what the business is trying to accomplish. So this is an example of integration from a Nutanix perspective. This is something we're working on them currently with in terms of integrating directly into their Prism console. So you have, within Prism, you have the ability to launch essentially a Plexxi management dashboard that not only tells you the health of your network, but also tells you how your traffic is distributed across the network, and we'll look at that a little bit more actually on the next slide. So this is a blown up view of that, what we call our visualizer. And it's pretty unique in a sense because when you talk about things like compute orchestration or storage orchestration, generally if I talk to a VMware administrator and I say, okay, how are you allocating your VMs? Is it, if I need a new VM for something, is it a random process where you say, hey, I need a VM, and it just gets spun up anywhere? And generally the answer is no. There's some logic to how it's spun up, whether I need specific, I need to put it where I have capacity from a CPU perspective, or where I have space in my data center, or my heating and cooling needs to be balanced out. Generally, the notion of orchestration takes into account these things from a compute perspective, right? Same thing with storage. You wouldn't necessarily go and allocate new storage LUNs on a device that already is out of space, right? You would actually look at where I have space and go do things that have some knowledge to it. It turns out in networking, that's not the case. In networking, when you place traffic across a fabric, essentially it's a random process. And that's, we joke about this because literally in the networking world, the best answer we can come up with is random, right? That's really what the networking industry wants you to believe. And what I mean by that is when I send traffic from a host that's sitting in a rack to a top of rack switch, it gets placed on an uplink into that spine layer. That process is a random hash, right? That flow gets placed on one of the available uplinks based on a hash. Nothing to do with if this link is oversubscribed or undersubscribed, if this traffic is sensitive or non-sensitive, needs to be isolated, non-isolated. None of that goes into account. It's just randomly placed on one of those links. So there's all kinds of problems with that just from hey, I really need to have better control over it. But the biggest issue is I need to know what my network capacity looks like at any given time, and if I'm placing things randomly, how would I ever know that? So one of the things we give our users is this notion of a visualizer, which is the edges around the circle are essentially the switches in the Plexxi fabric, and the middle is essentially a heat map that you can go and very quickly look at and say, okay, this pink color happens to be all part of the same workload. So now I know where the traffic, and in this case, this is specifically the Nutanix cluster VMs. So I can go look at that and say, oh, I know exactly how my cluster VMs are being placed. And not only that, I can look at this heat map and say, on a given switch, I know which ports are getting more congested versus other ones. So I can see the green ones are perfectly fine, but there's some red ones in there. And I may want to go and drill into those and figure out what's going on there. I may need to allocate some more ports there. So this is something that is really, really, really complex in normal networking. Because we built a system that is deterministically placing traffic, not randomly, and we're doing all of this in software, we can give you a much better view, and then we can go integrate that back directly into the hyperconvergence systems management console. We also have the ability to build standalone dashboards. This is an early snapshot of a new product we're going to be announcing in about a month or so. It's based on Elasticsearch, which is a open source platform for collecting machine data. And so what we're doing is feeding Plexxi switch data into this, not just syslog data, but also flow statistics from SFlow into this. And we're building these dashboards to allow our users to actually go and, again, easily visualize what their network is doing. And again, this is kind of custom tailored for a Nutanix environment where you can start to look at not only the traffic levels, but you can also dissect what that traffic is. Is it Cassandra traffic? Is it whatever? Within the Nutanix system itself, you can kind of look at more details and start to drill down. So the big focus here, when we get beyond the networking piece of our solution, we talked about the switches and we talked about the control layer, being able to tell the network what you want, not how to do it. But the other big layer is really the integration layer, and that's how we're accomplishing a lot of this lights out integration with the hyperconvergence vendors or the IP storage vendors. And really what that looks like is something like this. It's actually an entire layer in our suite called Plexxi Connect. It's built on an open source platform called ST2, which is being heavily used in some of the big cloud players right now to do what's called event-based workflow automation. It's a very fancy way of saying, if I detect something, here's what I do, right? It's a if-then-that kind of construct for infrastructure automation. It's getting people away from complex spaghetti code of scripting, which is really how a lot of automation is done these days, where you start out with a simple script, and then all of a sudden you have to extend it to go do something else, and all of a sudden you're maintaining thousands of lines of scripting, and anything you change breaks everything else. The notion of event-based workflow automation is that everything is decomposed into single events, and I can now go quickly do lots and lots of those, and if something needs to be added, it becomes a lot less impactful on everything else. So this is a product that we're shipping now, again, based on an open source platform. And it allows us to build all of these integrations that you see on the left into these common infrastructure platforms, whether it's Nutanix or VMware or OpenStack, it doesn't really matter, but that's what we're focused as a company on, building pre-built integrations into these things. We understand how the product works, what events it generates, and what that might mean for the network, and we make sure those triggers reflect what the network might want to do. All of that's customizable, but we build it so it's off-the-shelf usable. And then there's a community of folks in the ST2 community building different types of DevOps and what's now called ChatOps types of integrations that now become available to our users. So for example, we like to talk about this a lot because it's kind of cool, but we can actually operate a Plexxi network from Slack. We have a Slack channel. You can type commands in and tell the network what to do. It'll tell you things back if it's done it or it hasn't done it. That's really, it's a really powerful example of how you can now start to tailor the workflow for your network into a very customized way that works for your organization. And this is being extended all over the place with folks that are really heavily into DevOps and ChatOps. So again, our focus is really on these infrastructure level integrations, converged infrastructure, storage, and big data. A lot of the DevOps things are really, again, being enabled by the community. And the goal here is that as much as possible, the network should be the least of your concerns. It should do as much as it can by itself. It should let you know when it needs help, needs a human to make a decision, and it should give you the right information at the right place to make those decisions. So this is really kind of a wrap up here, but again, our focus, what is, again, coming back to the point of the talk, what is the network's role in hyperconvergence? First thing, it's got to be a single tier. You can't go hyperconvergence and then build a network that's multi-tier and complex and scale up. It's got to be a single network, but still have the ability to be partitioned when your workload requires it. And it's got to give you one view. So really, this is our notion of hyperconvergence. A quick on who is Plexxi. So one of our investors, actually our latest investor, is Google Ventures. Generally, Google does not, people talk about Google a lot in the networking world about how they're building their own switches and things like that. They also understand a lot about networks because they've taken the time to essentially design their own switches, stop dealing with branded switch vendors, build the software that goes along with it. So they've really become experts at what is going on in the network. And they realize that the network is kind of when we talk about where computing is going, computing is really a distributed compute problem that is really reliant on the network. So it was really a big validation for us when they invested in Plexxi, because we're the only networking company that they've ever invested in. And they realize that some of the things that we're doing are really helping to unlock some of this future. So we're focused on not just hyperconvergence IP storage. A big part of our business is also on building out larger scale public and private cloud infrastructures. That's a lot of what we do. We've raised about $90 million to date, again, from folks like Google, Lightspeed, Matrix, Northbridge. And we're on a fairly fast growth path right now. We're adding a lot of big customers. We have some large scale X as a service infrastructure, or basically software and platform as a service customers, some service providers, and some large federal agencies that are deployed with us. And our focus right now in the enterprise space is really around partnerships with hyperconverged vendors and IP storage platforms. Our newest platform is the last one I talked about, the Plexxi Connect, which is part of our overall solution, again, focused on making it really easy to automate what the network does for you based on your environment. And that's it. So thank you very much for attending.